What is time? How does gravity work? What is the universe made of? My kids ask me these sort of questions all the time. And I'm sure many of you have been likewise bombarded by similar queries from your own budding young scientists. But nonetheless, these questions really are some of the most fundamental in all of physics. And yet their answer continues to elude us. I would like to share with you how my team and I are harnessing the extraordinary properties of lasers to unravel the mystery of space and time in the universe. So a laser is more than just a lamp that shines light at a single color. The light waves from a laser reinforce each other, making it possible for the beam to travel incredible distances without spreading out. In fact, if I take this laser and shine it at Otto's magnificent whale skeleton here, you can see a tiny but very bright spot. On the other hand, if I shine this flashlight, the beam spreads out quickly, and by the time it gets to the skeleton, it's not even visible anymore. So if I were to take this laser and step outside right now and shine it straight up into the sky, making sure to avoid any police helicopters, of course, the beam would reach all the way to space. So one of the things we can do with a laser like this is to add a data signal onto the laser beam and create a laser communication link. This is exactly what we plan to do with a laser and this telescope at the University of Western Australia. We're going to set up a laser communication link between the Earth and the Moon. And so when NASA lands the first woman and the next man on the Moon in a few years' time, we can help receive and broadcast to the world the high-definition video footage of their first steps on the lunar surface. Now, as cool as that is, I'm here tonight to tell you about something even more amazing we can do with a laser beam shot from this telescope to space. And that is to try to understand the true nature of space and time. Almost everything we can see around us can be described by two laws of physics: Einstein's general theory of relativity and quantum mechanics. General relativity describes the universe at large. It tells us how gravity moves objects through space, like planets orbiting the sun or an apple falling from a tree right here on Earth. But it also tells us how gravity slows down time. Quantum mechanics, on the other hand, describes the cosmos at its smallest scale, including atoms and molecules and how they interact with each other. Quantum mechanics underpins virtually all of modern technology, from the transistors found in smartphones and computers to specialized quantum machines, including the ultra-stable atomic clocks keeping time on board GPS satellites in space. Now, even though these two are our most successful laws in physics, we know there is a big problem. They are incompatible with each other. Quantum mechanics doesn't include the force of gravity, and the maths used to describe time and space in general relativity breaks down at small scales. We've now reached an impassable chasm in our comprehension of the universe. We know that our laws of physics will need to be changed for us to be able to understand the true nature of the universe. We just don't know how. So what can we do to try to unravel this mystery? We need an experiment where gravity can interact with the quantum world. Because we know that if we can look close enough at time or space, we're going to find a place and time where our predictions no longer match what we measure. Now, remember before that I said gravity doesn't just make apples fall from trees, it also slows down time. Well, we can use this information when we build our experiment. So it turns out a clock experiencing gravity on the surface of the Earth actually ticks slightly slower than a clock floating way out in the depths of space. Now, this might seem like an extraordinary claim, but it's true. In fact, you verify this claim every time you use Google Maps. When you navigate using GPS, your phone calculates your position on the surface of the Earth by triangulating timing signals received from multiple GPS satellites in space. Those timing signals are generated by quantum vibrations of atoms in those atomic clocks on board those GPS satellites. Your phone's calculation takes this slowing down of time into account. This gravitational time dilation, as nerds like me like to call it. If it didn't, your position would vary wildly. It would drift by 500 meters every hour. Armed with this information, we can build our experiment. We can set up one atomic clock on the surface of the Earth and another out in space. We can measure the time dilation between them and then look for tiny deviations not predicted by general relativity. If we find them, then we found that clue that we need that tells us how our laws of physics need to be changed. Scientists around the world have tried this experiment, but so far their search has come up empty. Good news for us. A few years ago, a new type of clock was invented, optical clocks. Now these clocks tick 50,000 times faster than those on board GPS satellites at the moment. And that's important because the finer we can slice up time, the more precisely we can make the time dilation measurements. And this is where lasers being shot to space comes in. We can set up one of these optical clocks on the ground and transmit its timing signal up through the atmosphere to a second optical clock on a satellite, effectively creating a laser timing link. At the satellite, we can compare those two timing signals and look for those tiny deviations not predicted by general relativity. Sounds pretty easy, right? There's one more thing that stands in our way. Earth's pesky atmosphere. Well, actually, it's pretty good because we need that air to breathe. But it is bad for our laser timing link. And to understand why, we must turn to one of the most serious pieces of scientific literature, the song Twinkle, Twinkle, Little Star. Stars appear to twinkle because light is bent by turbulence in the atmosphere, hundreds of times per second. I'm sure you've all seen the most well-known example of this, the heat haze rising off a hot road in summer. But even under the best conditions, the atmospheric turbulence also changes the laser light time of flight, making it impossible to make timing measurements between two optical clocks through the atmosphere until now. A short while ago, my colleagues and I came up with a new idea. We can take our laser signals and send them one way through the atmosphere and reflect a little bit of the light off a tiny mirror on a satellite hundreds of kilometers away and then detect that light back on Earth. By comparing the light waves of the outgoing laser beam with the light waves coming back, we can measure changes in the light travel time faster than the turbulence can change the atmosphere. And just like noise-cancelling headphones, we can make variations to the timing of the laser beam going out to cancel out this atmospheric timing noise. So by the time the beam gets back to the satellite, the turbulence effect is gone. So where do we go from here? We have to test our technology to make sure it works as we think. So with this in mind, we set up a laser timing link 2.5 kilometers in distance between two buildings in Perth. And we made a measurement over this link. Now, it turns out because the atmosphere thins out really quickly as you move up, this relatively short horizontal link actually has the same amount of turbulence as the link all the way from ground to space. And over this link, just earlier this year, we made a laser timing measurement with a precision 10 times better than the best optical clocks, setting a new laser timing world record. We are now ready to set our sights and target our lasers towards space. To do this, my team is setting up the first ground station in the Southern Hemisphere. And we're going to use it to make the world's first laser timing link between ground and space. The heart of this ground station is this optical telescope. In this time-lapse video, you can see that the telescope can find and follow satellites as they move over the Earth. Once the telescope has locked onto a satellite, it looks for a laser beam coming from the satellite, steering itself as the satellite passes overhead, as is shown here in this model satellite that my colleague's holding here. Over the next year, we're going to trial this technology by flying aircraft over our ground station in a way that mimics satellites passing overhead. We've already started experimenting by having laser links between the ground station and a drone, which can fly about as high as 1 kilometer. After this, we'll set up laser links to aeroplanes that can fly up to 5 kilometers high. And finally, to stratospheric balloons that can reach to the edge of space. If these trials are successful, we will have proven that this Australian-developed laser technology is ideally suited for measuring time dilation between ground and space. And so when the first optical clock launches in a few years' time, our technology will be ready to help us answer the most fundamental questions in physics and reveal the true nature of space and time. Thank you.